of all the cosmological phenomena discovered by our civilization, nothing compares to the sheer magnitude of one of the universe's most powerful events. A gamma-ray burst, or GRB, is an extremely energetic burst of gamma-ray light observed from distant galaxies as far as 8 billion light-years away, yet energetic enough to interfere with Earth-borne satellites and astronauts. Hundreds of times brighter than a supernova, and nearly 1 million times as bright as our sun. An individual burst can last for milliseconds, while some range up to several hours. They are powerful, releasing massive amounts of energy in the matter of a few seconds, equivalent to the amount that the Earth's sun will produce during its entire 10 billion year lifetime. Fortunately for life on Earth, GRBs are rare, with only a few occurring in a galaxy every 1 million years. Scientists remain uncertain as to what causes this explosive phenomenon, though several developing theories persist. GRBs are the universe's most brilliant electromagnetic events identified by our civilization, and though only observed from astronomical distances, astronomers theorize that a gamma-ray burst originating from the Milky Way is inevitable, with one occurring within the proximity of Earth, capable of initiating a global existential catastrophe. The history of GRBs dates back to the 1960s, during the height of the Cold War. The United States military suspected that the Soviet Union might be testing nuclear weapons in space, a violation of the Limited Test Ban Treaty prohibiting such activities. With no effective means to monitor one another, the states were quick to distrust their Soviet adversaries. After all warfare is based on deception. When a nuclear device detonates, it produces a flash of gamma rays, among other types of light and radiation, that the military could theoretically detect. Assembling a team at the Los Alamos National Laboratory, led by Roy Olson and Ray Klebesattel, the US decided to develop technology that might reveal treaty-violating activities. In the event that the Soviets were detonating nukes on the far side of the moon, or elsewhere outside of Earth's atmosphere. This resulted in the Vela satellites, specifically designed to identify these high-energy pulses. Olson and Klebesattel analyzed the data captured by Vela, searching tediously for any signs of Soviet detonations. In 1969, they noticed a flash of gamma rays captured 2 years prior, astounding the researchers, who noted that it did not seem to originate from a nuclear blast, which produces a very distinctive pattern of gamma rays. Additional mysterious flashes followed over the years, puzzling the military scientists who began to understand what they were dealing with. These were no ordinary space Russians. Scientists ruled out any other gamma light producing phenomenon occurring concurrently, such as a solar flare. And the source of these bursts was certainly not emitting from the surface of the Earth. They settled on the notion that whatever these bursts of energy were, they originated randomly all over the sky, far outside the vicinity of Earth's orbit. In an ironic twist, the successful deployment of Vela revealed no illegal nuclear tests, but a far greater and foreboding mystery. Olson and Klebesattel's discovery was declassified and published in 1973, with 16 gamma-ray bursts officially confirmed since their initial detection in 1969. Their findings intrigued astronomers worldwide, who were puzzled by the notion that something unknown, far within the vast cosmos, generated such high-powered bursts of gamma rays, a concept almost out of a science fiction story. Scientists understood that significant celestial events could release troves of gamma-ray energy, such as the explosion following the death of a star, or an immense solar flare, but nothing that matched the scope and scale of what the United States military accidentally unveiled. They only knew that these bursts originated somewhere deep in the cosmos, unsure if from within or outside our galaxy, and no idea what was causing them, but that they were happening every year, or so they thought. GRBs became the greatest astronomical mystery for decades, while astronomers knew the resolution lied in the development of further advanced technology that might provide a faster response time to capture a burst's afterglow. In 1996, 30 years after the first detection, humanity achieved a breakthrough in this cosmic enigma. That year, the Dutch and Italian space agencies launched Beppo-Sax, a satellite designed to detect high-energy light from deep space and to trace its origins. In 1997, Beppo-Sax detected GRB 970228, pinpointing its exact origin and transmitting the data back to Earth, allowing for ground-based observatories to examine the afterglow. Following a burst's explosive flash, an afterglow produces the cooldown period following the release of a massive burst of energy, emitted at longer wavelengths such as X-ray, ultraviolet, and infrared. This event marked the first time a GRB's afterglow was ever observed, and tracing this particular GRB's origins from a faint galaxy 8 billion light-years away. Follow-up observations on past recorded GRBs uncovered similar findings, though many more questions surfaced. GRBs were erupting extremely far away, their detection by our technology an evident indication of their immense power. What exactly caused these bursts in the first place? Scientists speculated that comets colliding with neutron stars might be the cause. But since most neutron stars are found within the galactic plane, where all massive star formations transpire, this couldn't be the case, as a higher proportion originating from this region would be detected, rather than the seemingly random distribution astronomers observed throughout the sky. When a cosmological event generates an astronomical amount of energy, eventually a usual suspect takes center stage. Of massive stars collapse, the star explodes, producing a hypernova, an extremely powerful supernova. Soon afterward, a black hole arises, siphoning all adjacent matter. A proposed theory stipulated that when a hypernova erupts, instead of exploding outward, could perhaps channel the energy released from the exploding star inward, funneled like a jet or beam of energy. Further findings reveal that this was indeed the case. The cores of massive collapsed stars descend into the newborn black hole, forming an accretion disk, a magnetic field that captures neighboring matter, swirling from the disk away from the black hole's center, while emitting a twin beam of energy close to the speed of light, equivalent to the total energy of a supernova, cleverly quipped by some astronomers as a death ray, bright and powerful, and detectable from billions of light-years away. Scientists theorize that there are several types of GRBs, all of which vary in duration and intensity, implying that there may not be a single reason as to how GRBs function or are caused. The longer duration bursts are typically associated with hypernova explosions, while with short bursts, the scientific consensus finds the merging of neutron stars as the primary cause. When a binary system's stars go supernova, they remain in orbit together as neutron stars. When massive objects revolve around one another, their orbital energy slowly diminishes by radiating away gravitational waves. Caught in a dance of death, their inevitable clash culminating in the birth of a black hole, followed by an accretion disk, similar to a hypernova event, though lasting milliseconds. GRBs currently remain impossible to predict, as the science related to the end of a star's life cycle continues to elude astronomers. A GRB can fire off at any time, with one occurring nearby, oriented toward the Earth, capable of frying the atmosphere. The direct radiation from a GRB's jet, in the form of X-rays and gamma rays, poses no immediate threat to the planet, as the atmosphere absorbs most of these naturally. However, the long-term consequences to the exposed atmosphere marks the beginning of the end for its planetary inhabitants. A hypothetical influx of X-rays and gamma rays would cause our atmosphere's chemical composition to change, depleting the ozone, allowing for an increase of ultraviolet radiation at sea level, while reducing energy received from the sun, a chemical cocktail of destruction that could decimate most forms of life on Earth. Some scientists consider that one of Earth's 5 major mass extinction events might have been the result of a gamma-ray burst. Upon observing the fossil record of the Ordovician-Silurian extinction event 440 million years ago, species living near the sea level extinguished faster than those living deeper within the ocean, possibly due to ultraviolet radiation. As the deep-dwelling species survived for longer, Earth's water shielding them from the radiation for a time. This pattern was not observed in any other known mass extinction event, signifying a GRB as a possible offender. The OS event ushered in an ice age, and similar to most mass extinctions, the change of the climate had much to do with it. The OS was a warm period, and the sudden glaciation of the world is difficult to explain without a causation, which some theorists point toward a reconstruction of the Earth's atmosphere, the onset of this glacial period initiating as the sun's energy was absorbed, obstructed by an altered atmosphere. Of course, the scientific consensus regarding the exact reason of the Ordovician mass extinction event remains unknown. Our current technology detects at least one GRB per day, with the closest instance occurring in March of 2014, 130 million light-years away. Some estimates, based on the amount of GRBs detected from other galaxies with similar star composition as the Milky Way, suggest that the Earth may find itself in the path of a GRB once every 10,000 years, with no method to detect if our planet falls into the wake of an oncoming burst until it actually happens. And as humanity continues to map out the stars, several findings reveal that a number of stars at the end of their life cycle, in proximity to our solar system, might be potential candidates for a future gamma-ray burst. One such star lies 8,000 light-years away, well within the danger zone. Wolf-Rayet, or WR-104, a massive star, a part of a binary system, resides in the final phases of its life cycle, hundreds of thousands of times brighter than our sun. The binary orbit of Wolf 104 produces a brilliant spiraling nebula, with the star's axis guiding the entire system with an orientation aimed at the Earth. If a supernova was to occur, with a gamma-ray jet emerging, our civilization would find itself right in the center of its firing line. However, the Keck Observatory indicates that the binary system's orbital axis isn't quite pointed directly at the Earth, which might put our planet just shy of the burst's destructive path, offering an epic cosmic light show in its stead. Though impossible to tell when a star will burst, many speculate that Wolf-Rayet may have over 500,000 more years left, ample time for our species to develop a solution or an escape plan. In the meantime, further developments over the years continue to sharpen mankind's ability to better understand this phenomenon. With Bepo-Sax ceasing function in 2002, NASA launched the Neil Gehrels Swift Observatory in 2004, formally designated the Swift Gamma-Ray Burst mission, which proceeds with its mission to date, responsible for over 1,000 GRB detections as of 2015. Optimized to detect and ominously slew toward a fresh GRB afterglow, Swift's sensitive gamma-ray detector aims to determine a GRB's origin and cause, while conducting all-sky surveys, transmitting its discoveries to ground-based facilities. In 2008, NASA launched the Fermi Gamma-Ray Space Telescope into low Earth orbit, equipped with the Gamma-Ray Burst Monitor, an instrument designed specifically to study gamma-ray bursts, detecting several hundred per year. These two monoliths of human ingenuity serve as a testament to our civilization's prowess, yielding discoveries including the brightest and farthest objects ever observed by planet Earth's astronomers. Our technological revolution sails deeper into the 21st century, with the best yet to come. Gamma-ray bursts. High-energy jets of radiation blasting their way through the universe, happening deep within the cosmos. They are highly energetic, capable of massive destruction, with their explosions releasing tons of gamma radiation. So far, we know they originate outside of the Milky Way, with several theories as to their origins, but scientists remain uncertain as to the nature of these fully armed and operational bursts of energy.